Welcome from my side. I talk about the condition monitoring of CNC machines and hardware accelerators to make it more efficient and faster. Just a quick introduction from the application side of things, or from the perspective what happens if we don't do this. Wind turbines are really important for us, as we've heard, for sustainability, for clean energy, for everything. And one of the reasons why they fail quite regularly is because of the bearings. The bearings are manufactured using a CNC milling, and if the surface quality in the fabrication process does not meet the standard or the quality requirements, the bearing will fail prematurely, which leads to downtime of the wind turbine, which will lead to no energy produced by this wind. And as we can see, we will need more wind energy in the next years, meaning that the demand for those bearings will also increase. Going to the fabrication process, to the CNC milling, we can determine the level of wear on our tool by just measuring how far the edge of the tool has been driven back during the process. We call this width of wear. For the Germans here, Verschleißmarkenbreite, that's why it's dB. And it's basically the distance in millimeters, how far this edge has been driven back. The standard way to measure this or to determine this level of wear is to do a visual inspection, a manual visual inspection on the machine itself, which means that a technician has to open up the machine, check the tool, and then replace it or not. So this means either the tool is replaced too early or too late, which leads to either increased cost of maintenance if you exchange it too early, or defects in the produced goods if we exchange it too late. So in our work, what we focused on is using vibration data to get this width of wear using AI. And we've developed specialized hardware accelerators, which is more my part of the work, to accelerate it. The database that we've collected on CNC machines are basically, as you can see in the setup. So we have introduced our sensor unit featuring some acceleration sensors and used it to collect 795 recordings of a length of 2.1 seconds of just one-dimensional cuts of this steel block that you can see there. As I mentioned, the width of wear is usually determined by visual inspection. So we couldn't open up the machine every 2 seconds to perform a measurement. Hence, we had to do some fitting to determine the parts in between those measurements. The neural network that we used for determining this level of wear is basically a convolutional neural network, a CNN, that we've implemented using our standard Python tool chain that we use for all kinds of machine learning approaches, and then optimized it using a hyperparametric grid search. And we came up with this structure. Basically, we have 5 convolutional layers. We use one global average pooling layer and then 6 dense layers for the final result. And we use 16-bit quantization, which is important to make it more hardware efficient. As you can imagine, if we were using a 32-bit floating point, that would be a huge computational effort for the hardware. To compare it later on to our accelerated version, for the first step, we have transferred it into C code, C software, using RISC-V, which is a commonly used library. Coming to the accelerator design, which is really my part of the work. I'm a digital designer, and usually we work with HDL languages to describe our hardware. So we wanted to get from our model implementation in Python to a Verilog accelerator. One way to do this very efficiently is using high-level synthesis. In this case, we first translated the Python model into C++ and some pragmas using the open source library HLS4ML. And then in the second step, we translated this C++ code and pragmas into Verilog HDL by Vivado HLS. Vivado, probably you know that, is a tool from Xilinx, which is specific for Xilinx FPGAs, which I talk about later in my conclusions. We've performed multiple optimizations to make it more efficient. Particularly, we've worked a lot with the hardware we use. and optimized in two ways. Once for latency to get the result of our computation really fast, and also for resource efficiency to get it into hardware most efficiently and to use less of our logic parts than we used FPGA. The basis platform that we always use in our group is the RISC-V processor. RISC-V is an open instruction set invented at the University of Berkeley and has been around for about 10 years now. The AI RISC, our implementation of this open instruction set, is open source available on GitHub. You can see it in the upload here. You can also check the references in our paper, and you can just download it and use it in your projects if you want to, or also collaborate with us. We focus on having a modular adaptable structure so that we can adapt our processor core to the application, and we feature the 32-bit instruction set of RISC-V with the complete packages that you see here. Specifically interesting for all those of you who are doing machine learning, CP extension, the digital signal processing extension that also features single instruction multiple data operators. In most cases, we deploy our solutions for research projects on FPGAs. One example is the Nexus video board that I would really recommend you to use because you have both programming port for the FPGA, but also an additional JTAG interface to program the microcontroller. And as you can see, the neural network accelerator that we've developed for this work neatly fits into our system using the AHB light bus and also some interrupts to get the signals in and out of the accelerator. Yesterday, my colleague presented already a poster on the topic, how he has designed the algorithms. Basically, the CNN achieved a root mean square error of 4.27 micrometers, which is very sufficient. As you can imagine, if we're measuring the width of wear in the area of 1 to 2 millimeters, something like that, then this is quite precise. As I mentioned earlier, we have one version of the CNN for the accelerator that is optimized for latency. And as you can see in the table below, we have reached a reduction in runtime clock cycles of 99.93%. For all those of you who have worked with hardware and with software, this is quite understandable because when we process everything in hardware, we don't need to transfer the data from the memory to the core and from the core back to the memory. For the latency, for the resource optimized implementation, we have achieved still a latency speed of 99.4%, which is also significant. And when you look at the hardware resources in the particular FPGA that we've used, the difference is also quite significant, especially if you look at the digital signal processing blocks that were used. Then you can see that the more resource-oriented implementation has a lot of advantages in that area. This brings me to my conclusion that the CNN and the accelerators enable real-time tracking of the width of wear on our tool inside the CNC machine. So what we're transmitting out of the machine is only this value in millimeters and not all the raw data. The error of the method that we are using here is quite acceptable as it's just 0.3% deviation compared to the range of the values that we're working with. Unfortunately, there's also a couple of drawbacks when you look at this research project, which worked quite nice. But if you want to deploy it in the field, as I mentioned in my introduction, we've just used one-dimensional cuts of the steel rod. And there, the method works quite well. But if we imagine our CNC machine working on real products, the movements get much more complex. And it might be that it's much more difficult to determine this width of wear from the acceleration data, from the vibration. Hence, we want to investigate the performance in the field as well with our project partners and see if we can confirm our results or whether we have to change something about it. Looking into the future, we should definitely validate our method on more complex cut shapes and also to enhance our goals, which comes to latency, energy efficiency, and also form factor if we want to integrate it on the milling tool itself. Potentially an ASIC implementation would bring some benefits. Since I'm a digital designer, I'm always excited for ASIC solutions. However, if we are using a high-level synthesis approach, as we did here with Wiede HLS, this brings a lot of complications because the HLS tool is targeting FPGA implementations, and some of the code that it gives out is not even synthesizable. Besides the synthesizability issue, the license of Xilinx Vivado also don't permit you to use it in other applications. Therefore, a completely new toolchain would have to be required, and that's also something that we work on at our institute. We have a more open toolchain for high-level synthesis that is also synthesizable. Last but not least, I want to acknowledge that we have received funding by the Federal Ministry of Education and Research in Germany for our project, and I also want to thank our project partners that you can see in the picture here to enable us to work on the CNC machines that they are selling and developing. And yes, that's about it. Here's a couple of references. I would recommend you, if you're interested in the topic, also to check out our paper at the conference. And now I thank you for your attention